So in the last lecture, we discussed about rectangular waveguide. It was said that the rectangular waveguide or any waveguide, it actually comprises of a single conductor, hollow conductor, and it carries EM wave from one end to the other end. And because of the boundary condition, it is not going to support TEM mode, but it supports TE mode and TM mode. So TE mode and is TM and MNN. MN, it represents number of half cycles in X and direction. Okay, that is in the cross-sectional dimension of the waveguide. Now, today we'll find few things about the waveguide and we'll see a problem. Okay, so the first thing, dominant mode that is covered on the last time also. Dominant mode. So dominant mode is that mode in rectangular has largest wavelength, or you say the cutoff frequency is least. And waveguide works like a high filter. So there has to be what? One least frequency, cutoff frequency, below which the propagation of EM wave is not possible inside the waveguide. There is nothing but the cutoff frequency. So if I draw frequency versus output, so it will be like this. So that cutoff frequency, okay. But you see that MNN, TEMN or TMMN mode. So MNN, it can have different values. So there can be infinite field configurations. Field configurations here you can understand the way the field is going to distribute itself inside the hollow waveguide. So here M and N, it can have any value from 0 to any larger quantity, not infinite, but theoretically you can say infinite, and so N can have infinite options. But M and N cannot be 0. And this happens, there is motion in X direction and Y direction is going to happen only if TEM exists, but
sir, sorry to interrupt you.
Both 0.
Sir,
okay.
Your voice is
see, yes sir.
Your voice is breaking. Can you change your location?
Voice is breaking. Actually, sir, today location, this is the most
okay. Continue, sir.
But from today only I'm facing severe this connectivity. Because in the last week it was very fine, but yesterday I was not having any network at all.
Okay. Continue.
But we'll try to change the location, sir. I will come near to the window. Is it okay, sir, now?
Yes, sir. Now it is okay.
Hello.
Sir. Now it is okay.
Okay, sir. Now I will go to the next page. So here we'll see some of the formulas, and with the help of those formulas only we will try to explore more about the waveguide, and on the formulas discussed we'll see a problem. Okay, and in the first lecture one data sheet was shown to you. So the reason why the data sheet was shared, that also will be discussed today. So let us start. So first formula, you can note down the formula if you want, or if you're having any access, sir has already uploaded POSAR book, so you can get the formula from there also. Otherwise you can note from here. So first is the cutoff frequency formula. Since every waveguide is going to work like a high pass filter, so every waveguide is going to support some least frequency. There is nothing but the cutoff frequency. So that cutoff frequency is given by 1 by 2 root of mu epsilon, and in bracket here is m by a the whole square plus n by b the whole square. Okay, here m and n already have said that m and n both represents number of half cycle in x direction and y direction respectively, and both cannot be zero simultaneously, because if you put 0 0 here, so you can see that there is nothing like cutoff frequency. So that is going to happen only if TEM mode can exist inside a waveguide, but that is not possible. Now, with the help of this formula, we'll understand that what is the meaning of dominant mode. Okay, so here on the right hand side, I will draw the cross-sectional view of a rectangular waveguide. So this horizontal width of the waveguide is represented by B, height of the wave B, sorry. The width is represented by A and the height of the waveguide is represented by B. And this is the length of the waveguide. But cross-sectional dimension, it totally depends on the, the characteristic impedance, or this all reading fees. Everything depends on the cross-section. The earlier lecture also, if you remember, it was width of the strip, then width of the ground plane, okay, then dielectric material. So length part, it talks whenever you're going to consider the phase shift when a wave propagates from one end to the other end through a transmission line. At that time, the length matters. Otherwise, it is the cross-sectional dimension and the material used. Okay, so here you can see that the cutoff frequency depends on the cross-sectional dimension and mode. Okay, now let us consider TE10 mode. Here is TE10 mode. So here the meaning of M1 is what? M is 1. That is what? 1 half cycle in x direction. So the field will vary like this. Here it will have very dense field, and at the edges the field will be very weak. Okay, that is the meaning of 1. And 0, that is what? N is 0 here. So being 0 means what? There is no variation of the field in vertical direction. Means if I move from bottom plate to the top plate, the field will remain constant. Okay, it's not going to change. Now if I substitute this value here in cutoff frequency formula, so what I'm going to get? 1 by 2 root of mu epsilon, and it becomes 1 by a. Okay, because n is 0. And this can be further viewed as what? I can rearrange this to get, okay, we'll just move ahead in the same formula. So it becomes what? 1 by root of mu epsilon can be written as what? C divided by 2 times of A now. Provided that the medium inside the waveguide is what here. So mu is actually what? Mu r, mu naught. Epsilon is what? Epsilon naught into epsilon r. So mu r and epsilon r is going to be 1 if the medium is air. So let us consider that inside the waveguide, air medium is there. Okay, there is no, its dielectric medium is air. So in that case, the cutoff frequency becomes what? C by 2a. Okay, now let us another case. There is TE01 mode. Now out of these two, we'll see under which situation the frequency is going to be lesser, and whichever will be the least frequency for a particular mode, that mode will be called as what? Dominant mode. Okay, so TE10, once again, if I go for the formula, will now M0, so it becomes 1 2 root of mu epsilon. It becomes by B. Here it's divided 2 times B. Now we are having that A is larger than B. Generally, A of if to design, then you take A as 2 of B. So here, since it's smaller, the frequency here I will write 1, and here frequency because of zero mode is of 01. So you can see that the cutoff frequency is lesser for TE10 mode and TE0 mode. That's why this is the reason why the TE is dominant belongs to what? Okay, so we'll move ahead. The second formula. Now this was, the earlier was the cutoff frequency. Next is beta inside wave. That's why I've written here. We are knowing that the beta represented omega root of mu epsilon. But here the beta is actually dependent on the frequency because the waveguide, it acts as a high pass filter. So one additional term will get involved here. So derivation is not required. Only have to remember the formulas so that you can solve design based problem. Now here there is omega root of mu epsilon. This is the basic formula for the beta from EM theory. That is, but that is applicable only for TEM mode, not for TE mode or TM mode. Okay, so to make it applicable, some modification is done as per the boundary condition offered by the waveguide. So the additional term is root of 1 minus fc by f the whole square. So here you can see that if your operating frequency, that is f, is larger than fc, then the beta g is going to be real in nature. Now if we remember the propagation constant gamma in any medium is given by alpha plus j beta. Okay, means what? It comprises of attenuation constant and the phase constant. Okay, since we are dealing with a waveguide, I will write it as what? Alpha g, and here is beta g, and this will be gamma g. So if the solution tells you that beta is real in nature, it means that in that medium the wave can propagate. But if the beta g, it becomes imaginary, so it is already imaginary quantity, and beta g, if suppose it turns imaginary, so imaginary into imaginary, it will become real in nature. It means that in that particular medium the wave cannot propagate. For example, in this formula itself, as long as your operating frequency, that is f, is larger than cutoff frequency, then this root will be what? The result from the root will be real in nature, and you can assume that the wave is going to propagate. It means that your waveguide is behaving like a high pass filter, and your filter, if it is operated above cutoff frequency, then there will be propagation of signal from one end to the other end of the waveguide. Now let us assume the situation changes. If operating frequency becomes smaller than the cutoff frequency, then what is going to happen? So here you can see that fc by f, that ratio, it will become larger than 1. So it becomes larger than 1, then the root will give what? Some imaginary terms to you. Now that beta g, which is already imaginary quantity, now it will become imaginary for second time. So imaginary into imaginary. So it will, this beta, it will become what? Real in nature. So you can say that when the beta becomes real in nature, it means that the wave is now facing attenuation, and that particular signal cannot travel inside that transmission line. So using this relation also, you can prove that waveguide, it actually behaves like a high pass filter. Okay, so but you have to remember that this is the formula if you are interested to calculate the propagation constant or the phase constant actually, then this will be the formula. Next is phase velocity. Okay, so phase velocity inside a waveguide. So phase velocity, it is represented by what? Vp. Now Vp here, it represents phase velocity in open medium, okay, unbounded medium. If that is divided by this additional new term, so everywhere you will find that all the formulas which I'm going to list here, that is taken from the EM theory only, but with this additional term. This additional term will get involved everywhere. It is coming because of the boundary condition offered by the waveguide. So it is Fc divided by F the whole square. So you can say that the phase velocity of unbounded medium, if that is divided by root of 1 minus Fc by the whole F the whole square. So it becomes phase velocity inside a guided medium. So as long as your operating frequency is larger than the cutoff frequency, the phase velocity will be real in nature. Otherwise, it will become imaginary. And the imaginary phase velocity is assumed as what? That the wave is not propagating. So you have to remember this formula. Another is what? Which is connected with the phase velocity only. There is nothing but the group velocity. See, phase velocity talks about the speed at which the phase is traveling inside a waveguide. But the group velocity talks about the speed at which the EM energy is traveling inside in any medium here. So here particularly we are talking about the guide, so waveguide. So it is just like your phase velocity only in the unbounded medium. Now this additional term, it is multiplied here. So 1 minus Fc by F the whole square. So that term which was earlier dividing the phase velocity, now this is getting multiplied with the phase velocity. So if we'll compare the two formulas, so you can see that the group velocity is smaller than the phase velocity. So phase velocity can be larger than the group velocity. That is the conclusion. Group velocity inside guide. And if you consider that inside the waveguide there is an air medium, so of course the phase velocity will be what? Equals to the speed of light. There is 3 into 10 raised to 8 meter per second. So inside the waveguide, the phase velocity will be larger than the speed of light, whereas the group velocity will be smaller than the speed of light if it is air filled. So remember that the phase velocity can be larger than the speed of light, but the group velocity will be always lesser than the speed of light. And if you'll take the product of these two and if you'll take the root of that, then it will be always equals to 3 into 10 raised to 8 meter per second. So if you have any doubt, you can ask. Okay, fine. We'll move to the next two formulas and the list of the formula will get over. Since we are talking about a transmission line, every transmission line, it has got some characteristic impedance. So the characteristic impedance here is written as ZG because waveguide. So guide is there, that's why ZG. And we are talking about what? TE mode, because as depending on the mode, the characteristic impedance changes. So here it is for TE mode, any MN for any value of MN. For TM, it is different. Formula is different. So it is given by what? Of free space or any depending on the medium. This N is nothing but the characteristic impedance of a medium. Okay, that divided by root of 1 minus Fc the whole square. For TM mode, there will be product of eta and this root part. That will be the change. So here you can see that the characteristic impedance of the waveguide will be larger than the intrinsic impedance of any medium. So eta is going to be 377 ohm if the waveguide is air filled. That divided by root of this part. So you can once again consider that if the operating frequency is smaller, that is what F is smaller than Fc. So impedance will become what? Imaginary. And the property of the imaginary impedance is that it never stores energy. It will reflect. So if you try to force a wave to propagate through a waveguide, but the operating frequency is lesser than the cutoff frequency, then the impedance offered by the waveguide for that particular wave will be imaginary in nature, and because of which all the wave will get reflected back. It will never travel inside the waveguide. But remember that this is for TE mode. For TM mode, you have to take the product of these two terms. That will be the only change. The rest of the formulas, they can be taken as it is. Now, the last one is guided wavelength. There is wavelength inside a guide. So wavelength is different inside a waveguide. It is given by wavelength. This wavelength is the wavelength calculated in unbounded medium by using C by F formula. But C you can take only if you're talking about the air medium. Otherwise, it is phase velocity divided by the frequency. Okay. Now, this term divided by 1 minus Fc by F the whole square. So here, the conclusion of this lambda g is that wavelength inside a guide is larger than the wavelength in any unbounded medium for the same signal. Like if suppose 9 gigahertz signal is propagating inside in open space, then the wavelength will be C by F straight away. But if it is inside the waveguide, then whatever wavelength you're calculating, that divide by this root factor, which is always going to be less than 1. So definitely the wavelength inside a waveguide is going to be larger than the wavelength in an unbounded medium. So these are the list of the formula which we have to remember, and based on this only we'll see one problem. So far, if you have any doubt or if you want if you have not noted down any and you want to know any of the formulas, I can go back. Otherwise, we can move to a problem. Do you have any issue? Hello.
Sir, can you please go back to the formula of phase velocity of a waveguide?
There is this. Wait. This is the velocity of wave.
So you're not
So it is. This is the formula for the phase velocity inside waveguide.
Okay, thank you, sir.
So it is phase velocity in unbounded medium divided by root of 1 minus Fc by F the whole square. So you can see here on the right hand side I have written that the phase velocity inside a waveguide will be larger than the group velocity, and it can be larger than the speed of light. Anything else? Should I move ahead?
Yes, sir.
So can you go back one more slide?
Okay. This is the first formula, cutoff frequency.
Yeah,
Formula is there, and with the help of this formula, we learned about what is the meaning of dominant mode.
Yes, sir, I'm done. Thank you.
Okay. Okay. So we'll move to one. Okay, so we can note down the data. The waveguide to calculate attenuation, because the wave propagating in the medium is lossy. Okay, so if the wave passes through a lossy medium, how much attenuation of that wave is going to take place, that depends how much length the wave has traveled. So length is brought in the picture only if we are going to talk about the phase or loss. Okay. Now, this waveguide, it is having a width of 7 of 3 cent. This from Samuel Live, okay, in the book Microwave Devices and Circuits. It's a solved problem only. Okay. Dimension in centimeter. What is asked that you find first thing which you are asked to find out. Okay, so one by one we'll do. First, I will go for frequency, but see, cutoff frequency you cannot find out unless until the name is disclosed to you, like whether you're asked to find out cutoff frequency for T mode or for TM mode, and if nothing is mentioned, so you go for dominant mode only. Remember this. If nothing is mentioned, what mode is propagating, so you consider that you are going to calculate cutoff frequency for the dominant mode, because generally the waveguides are operated for the dominant mode only. Just because you can use your waveguide or operate your waveguide for a smaller frequency also. Of course, that frequency will not be less than the cutoff frequency, and that comes from the kind of mode and the dimension. Larger dimension means larger wavelength. Smaller the dimension means smaller.
सर आपकी वॉइस नहीं आ रही है.
Abhi, what can I do? Because this is the second location and facing network issue from last day only. Okay, thoda more change karte. Now is it okay? Am I audible?
Yes, sir.
Sir, but you might have to repeat because कुछ समझ नहीं आता.
ठीक है, अभी फिलहाल मैं standing position में हूँ. Okay, so what I said that you are asked to find out cutoff frequency for a given waveguide whose width is 7 centimeter and height is 3.5 centimeter. Okay, means A and B both are given to you. So once again, I repeat that A is twice of B. So here you can see that 7 centimeter, which is what, twice of 3.5 centimeter. And the waveguide is operated for T10 mode. Your goal is to what? Find out cutoff frequency. So cutoff frequency ka formula was what? It is 1 by 2 times of root of epsilon. And inside this square root, it is m by a the whole square plus n by b the whole square. Okay, so n is 0. So finally what you get, it is C, because it is air filled. Nothing is mentioned about the this dielectric medium. Sorry, it is mentioned, it is air filled waveguide. So 1 by root of mu epsilon can be taken as what? C divided by 2. M is 1, n is 0. So it becomes root of m, that is 1, root of 1 by a square. So it becomes 1 by a. So this is the formula for the cutoff frequency. And if you substitute all this value, then you will get what? A frequency of 2.14 gigahertz. This is the frequency, cutoff frequency. So you will operate this waveguide at a frequency larger than this 2.14 gigahertz, because this is the cutoff frequency. This is the least frequency which can travel through this waveguide. If you are decreasing the frequency further, it will get reflected back. Why? Because the impedance will become imaginary in nature. If this part is clear, then we can move ahead.
Yes, sir.
Okay. Next one is determine the phase velocity of the waveguide. Okay, phase velocity of the waveguide when the operating frequency is 3.5 gigahertz is the operating frequency, and you are asked to find out phase velocity. Okay, so we'll move ahead. Now, phase velocity inside a guide. Okay, it is given as what? Phase velocity in a given medium divided by root of 1 minus fc, which you have calculated, and f square. So f is given. It is 3.5 gigahertz. And the cutoff frequency was 2.14 gigahertz. Okay, so fc is 2.14 gigahertz from the last calculation. So now first we'll calculate what is the phase velocity in a given medium. So medium inside the waveguide is air. So now let us consider that your wave is propagating inside air medium or in a air medium. So of course the velocity is given by what? 1 by root of mu epsilon. Since it is air medium, mu r and epsilon r both are going to be 1. So finally you get what is c, which is nothing but 3 into 10 raised to 8 meters per second, right? Now phase velocity inside a guide is given by 3 into 10 raised to 8 meter per second divided by root of 1 minus, now it is going to be what? 2.14 divided by 3.5, the whole square. Okay, giga will get cancelled out and you get 3.78 10 raised to 8 meter per second. Okay, so you can see that the phase velocity is larger than the speed of light. This is going to happen inside the waveguide. If anything you want to ask, you can ask her. Is there any doubt?
Sir, can you explain once again why this phase velocity is higher than speed of light?
Actually, I have not explained this part.
Okay.
See, temporary answer, there is of course, it's proper diagram is required for that, but it is going to be time consuming. So I will give alternate answer for this. See, the phase is not a physical quantity. Okay, like when I say age, so age is a number which represents uh, uh, something about you. It can be maturity, it can be your body proportion, like that, but it's a number actually. Okay, but age will never tell you what is the mass of your that person who is suppose 45 years old, because not you can guess कि इतना हो सकता है. But when I talk about the mass, it's actually physical quantity. But when I say age, so it is just for our understanding कि इतना age हो गया है, तो उसका body का feature कैसा रहेगा, क्या क्या हो सकता है. So similarly, when we talk about the phase is not a physical quantity. But when we talk about the energy, so it is a physical quantity there. You can measure it. Phase को भी हम लोग measure कर सकते हैं. That is okay, but it's not a physical quantity. So quantity which is not physically, which is not existing actually, it can travel with any speed. किसी भी speed से जा सकता है वो. That is the only reason why the phase velocity, it can be larger than the speed of light. But of course, अगर मुझे properly इसको अगर ये करना पड़ेगा, define करना पड़ेगा, so I need to draw few diagrams to understand it. which I don't want actually to do. But अगर आपको चाहिए तो मैं separately है ना आपको एक शीट पे उसका डायग्राम वगैरह ड्रॉ करके अपना गूगल अपना जो है कॉलेज का जो ड्राइव है उस पे मैं अपलोड कर दूंगा, so you can understand.
यस सर, वो कर दीजिएगा. एंड सर इसमें जैसा आपने बोला कि एज फिजिकल क्वांटिटी नहीं है, बट एंड सिमिलरली अपना फेज वेलोसिटी भी कोई फिजिकल क्वांटिटी नहीं है, तो यूनिट
No,
मीटर पर.
phase is not a physical quantity actually.
ओके ओके.
हाँ, velocity है मतलब of course like वापस मैं वही एज का एग्जांपल दूंगा. a person of 45 age is moving with certain velocity, तो of course तो एज तो है ही है उसका 45, बट जो velocity रहेगा तो velocity तो physically exist कर रहा है. एंड इट्स सुपरफिशियल आंसर. अगर मैं इसको एक्चुअल में अगर इस एग्जांपल को रिलेट करूंगा, एक काम करते हैं हम लोग, ये प्रॉब्लम फिनिश करते हैं, उसके बाद वी कैन टॉक अबाउट दिस. आई विल ट्राई टू यूज दिस व्हाइट बोर्ड एंड विल एक्सप्लेन इट व्हाई in what way the phase velocity can be larger. So this is phase velocity, that part is done. Next is what? Wavelength, guided wavelength. Actually the guided wavelength है ना, उससे आपको थोड़ा आइडिया आ सकता है कि phase velocity, how it can be larger than the speed of light, because wavelength, it is related with the phase only. Okay, wavelength roughly you can define as what? Distance between two consecutive phase, similar phase. That is nothing but the wavelength. Okay, so you have to find out now guided wavelength. If the frequency, you are operating your waveguide at 3.5 gigahertz, cutoff frequency you have already known, it is 2.14 gigahertz. So what can be the wavelength at that particular frequency? Means operating frequency. So guided wavelength is given by lambda g, that is equals to lambda in open space or in any medium, that divide by root of one minus fc divided by f the whole square. Okay, now this wavelength in a medium is calculated as what? C by f, because it is air filled waveguide, so I can use C divided by f. F is 3.5 gigahertz. Okay, 10 raised to 9, and this is what? 3 into 10 raised to 8. Okay, so from this you can find out lambda, and if it is everything is substituted there, so lambda g is going to be 10.8 centimeter. And lambda कितना आ रहा है? Lambda, if you have calculator, you can calculate, otherwise I will calculate this. It is 3 divided by 35. So 8.5 centimeter, 8.6 almost. This is 8.6 centimeter. So you can see that the lambda g is larger than lambda. So wavelength inside the waveguide, it expands. And this is actually related with your the phase velocity, how a phase velocity can be larger than the speed of light. So if you have any query, you can ask related to the problem. But you have to remember this list of formula. Now, I said that TE10 mode and TE01 mode, both are going to be what? Both are going to have different cutoff frequency. For TE10, the cutoff frequency is smaller than the cutoff frequency for TE01 mode, just because of some reason. But can you tell me when, under which case these two frequencies can be same? cutoff frequency for TE10 and cutoff frequency for TE01. If you have the formula, you can answer this question. Otherwise, I will show you the formula. And with reference to that formula, you can answer it. Where is this? A equals to B. Correct. Because here, if you remember, this was the result. Cutoff frequency for T10 mode and cutoff frequency for T01. So it is always C by 2, C by 2 in both the cases. Only A and B, they are different. That's why you are getting different frequency. So if A and B both becomes same, in that case, the cutoff frequency for both the modes will be same. Okay, means if you are having a square waveguide, then the cutoff frequency for two modes, they are going to be same. So such kind of modes are called as degenerative modes. Okay, so we have talked about what is the meaning of dominant mode, and the second definition, second term is what? Degenerative mode. So TE10 and TE01 mode, they are degenerative if the waveguide is square in shape. So degenerative modes are those modes which are having same cutoff frequency for a given waveguide. Another is the last this term, event-sent mode. I will write it here. So it is event-sent mode. So that mode which cannot travel through a waveguide, that mode is called as event-sent mode. But that is possible only if you are operating your waveguide below cutoff frequency. So any signal which is whose frequency is what? Less than cutoff frequency. So those modes are called as event-sent modes, and they will never propagate inside a waveguide. So we have got the idea about what is the dominant mode, then what is degenerative mode, and what is event-sent mode, and a list of formula with the help of which can calculate cutoff frequency, then phase velocity inside a guide, group velocity inside guide, then the characteristic impedance offered by a waveguide. But remember that there is no fixed characteristic impedance of a waveguide. That is the issue with the waveguide. कुछ fix नहीं है उसका. At different location, the characteristic impedance is going to be different. Okay, and of course it also depends on the mode. For every mode, you are going to have different characteristic impedance. So there is no fixed characteristic impedance for a waveguide. For one mode, you will have different cutoff characteristic impedance. For other modes, you will be having different cutoff characteristic impedance. Phase velocity inside a guide can be larger than the speed of light, but the group velocity will be always lesser than the speed of light. Now, if you want to ask anything, you can ask.